So part 2 of the Michelson-Morley experiment. And what we're going to do here is we're going to set it up actually using an airplane example. And the reason for doing that is it's just a little more intuitive for us. Sometimes when we do it with things we're not used to thinking about so much, for example, light waves, just the strangeness of the situation can give us some conceptual problems or challenges. And so we'll just do it with an airplane here. The analysis, though, will work exactly with light waves, and I'll explain why in just a second here. Let's set this up. So imagine we have an airplane. We're going from A to B and then back again. So a round trip, first leg up to B and then back down to A. We'll say our plane has some velocity, v sub plane, or we'll probably just use v sub p for the plane velocity. And then we have a wind involved. Actually, we're going to do no wind at first, but then we're going to turn on the wind, as it were. And the wind's going to go directly in the face of the plane on the first leg of the trip, and then it'll be with the plane, helping the plane on the return leg. So clearly on the first leg, when there's wind involved, the wind will retard the plane's velocity, so it'll be going a little slower. And just as, you know, if you've traveled by plane before, sometimes the pilot will say, hey, we have a tailwind today, so we're able to make the trip a little faster than normal. Sometimes we're battling headwinds, and therefore it'll be a little slower. That's what's going on here. So on the first leg from A to B, battling headwinds, and so it's going to be slower. The effective velocity of the plane will be the velocity of the plane minus the velocity of the wind. And then on the trip back down from B to A, then the plane will have added velocity because of the tailwind, so it'll be the velocity of the plane plus the velocity of the wind. Before we get into that, though, let's do the no wind case. In other words, how long will it take the plane to make a round trip from A to B and then B to A back again? Well, we know that velocity, or not velocity, but time traveled is just distance divided by velocity. Again, remember if you have to go, if you're going 60 kilometers, right? Let's just say 120 kilometers at 60 kilometers an hour. 120 kilometers divided by your velocity, 60, takes you 2 hours to get there, or miles per hour if you want to do miles per hour. So with no wind, then, the total time is going to be the total time of our trip. For one leg, it's the distance divided by the velocity, so just d divided by v sub p. So it's going to be d divided by the velocity of the plane. And then, of course, on the return leg, there's no wind involved. Same thing, plus d divided by the velocity of the plane, whatever it happens to be. And so clearly we can just add that together. We get 2d over v sub p. Okay, so that's the case. If there's no wind, we just need to know the distance. We need to know the velocity of the plane and simple calculation to give us the total time it takes for the round trip for the plane. Now let's turn on the wind. Okay, so we've got the velocity of the wind coming here. And actually, at this point, for those of you who want to do a little quantitative challenge, or even just conceptually for everybody to think about this, you think, okay, on the trip up, the wind's going to be against the plane, so it's going to retard it. It's going to take a little longer. On the trip down, though, the wind's going to be helping the plane. Shouldn't it cancel out? In other words, shouldn't you get the same answer for the total time? You know, definitely you're going slower on the first leg of the trip, but then you're going faster on the second leg of the trip. So should it not just cancel out and we get the same result? As we will find, it's not quite that simple. And so you might think about why that might be. You can think about it just in a qualitative, conceptual fashion. But you can also think about it for those of you who want to, say, pause the video now and see if you can work this out. I'll get you started by saying the velocity on the first leg of the trip is going to be the velocity of the plane minus the velocity of the wind. Okay, so that's the net velocity on the first leg. And then we have our same equation involved here, distance divided by the velocity. And the velocity on the second leg of the trip is going to be the velocity of the plane plus the velocity of the wind, v sub p plus v sub w. We use VW for the wind. The equation's the same. You just have a different velocity on each leg now. The total time is going to be, add those two things up and get the total time. So again, if you'd like the little challenge and see if you can come up with what we're going to come up with here in a minute, so we can do it correctly, then go ahead, pause the video, and try that, and then come back, and we'll look at the details here. Okay, so the A to B trip, the time, really what we're interested in here is the time. For that, again, is going to be the distance, d, divided by the velocity. And the velocity going against the wind is v sub p minus v sub w. So it's going to be d over v sub p minus v sub w. Just same equation as before, just different velocity this time. And then the B to A trip is going to be distance d, but the velocity in this case is v sub plane plus the velocity of the wind. So here we've got the time equals d v sub p plus the velocity of the wind. And the total time is just add those two things together. So the total time is going to be d plus vp minus vw plus d vp plus vw. Okay? And now what we'd like to do, here's where a little more of the algebra comes in, we'd like to simplify this a little bit. See if we can get it into a nicer form such that we can really compare it to this. Because remember, what we're maybe thinking here is that it should cancel out. Shouldn't this? It doesn't look quite like that, but shouldn't it maybe end up sort of like that? Well, it's going to end up not quite like that, but almost. So let's see if we can do that. So to do that, just to make some more room here, we're going to I'm going to bring this up here. We'll leave this up here because we want that result there. So we're still working with the wind stuff here. Okay, so we're saying here the total time, just rewriting this thing here, is going to be d vp minus vw plus d vp plus vw. And at this point, we've done the analysis. Now we just have to crank through the algebra a little bit and see what the result is. So this is one of the reasons we did the math reminder here. We have two fractions. We want to add them together so we can combine them. We need to get common denominators, and the little trick we use is we multiply each in the form of 1, but with the other denominator. So here's what we're going to do. We're going to say this equals d over vp minus vw times the other denominator in the form of 1, vp plus vw over vp plus vw, like that. Okay, so I'm just taking this first term here, multiplying by 1, but in a special form here, and do the same thing for the second term, plus d over vp plus vw, because that's this term here, and now multiply it by 1 in the form of the other denominator, vp minus vw all over vp minus vw. So I have not changed anything. I can also multiply anything by 1 if I want, and results will still be the same. But now you see in the denominator I've got vp minus vw times vp plus vw over here. Same thing over here, but just in opposite order there. So let's put it all together and see what happens in the numerator. So we're going to get, here we get d times vp plus vw all over vp minus vw, vp plus vw. Actually, I really should extend this over because I'm putting these two terms together. They both have the same denominator. That's this thing, just in a different order there, so I can flip it around. And then the second part of the numerator is plus d times vp minus vw. Okay, so I just combined them together. I haven't done anything else besides that here. But now I can look at the top and I can say, okay, I've got d times vp and d times vw. If I multiply that out. And over here I've got d times vp, but I've also got d times minus vw. So over here I've got a d times vw. Over here I've got a d times minus vw. They cancel out. I'll have dvw minus dvw. And I'm going to be left with d times vp here and d times vp here. So that's two of them. So I can write this as, try to squeeze it in down here, 2 times d times vp all over Vp minus Vw times Vp plus Vw. And we're going to bring it up here in a minute as well. Okay, so see what we did? We just said, okay, here's our total time, that plus that for each leg. Put them together for a common denominator, and then noted that in the numerator, some of the terms cancel out. So I've got d times Vw and then a minus d times Vw. So they go to 0, and I'm left with this. Okay, so now we'll bring this back up here. We'll leave that because that was our starting point. Okay, so what we've got so far then is 2d Vp over Vp minus Vw Vp plus Vw. So that's what we've got so far. Now let's, again, crank some more algebra here. Let's multiply this out in the denominator on the bottom here. So we'll leave the top as it is for a minute. 2d Vp. I've got a Vp squared. Vp times Vp is Vp squared. Minus Vw Vp plus Vw Vp. So those terms will cancel out. Minus Vw Vp here, and I've got a Vp times Vw plus Vw times Vp. And then minus Vw squared. If you've done algebra recently, you recognize immediately what we're going to get here, and that is this. Vp squared minus Vw squared on the bottom there. Okay, so, well, okay, now what? Well, again, going back to the math review we did in the last video clip, we're going to factor out in the bottom here, we're going to factor out a Vp squared. Okay? And so it's going to look like this. We got 2d Vp. We haven't done anything on the top for a couple steps here. But on the bottom, we're going to write this as Vp squared times 1 minus Vw squared over Vp squared. Okay? I just pulled out the Vp squared term here, so that gives me the 1 there, and then on the other term, Vp squared times that would give me the Vw squared again, so they're identical there, they're equal. And the reason I did that is now I can cancel this Vp on the top. I've got a Vp on the top, I've got a Vp squared on the bottom, and so this thing then equals, we'll write it up here, 2d Vp, oops, sorry, not the Vp, that's what we're trying to get rid of, 2d on the top, that's what I've got left on top. On the bottom, I've left one Vp here, so I've got a Vp, and then the 1 minus Vw squared over Vp squared. And we'll rewrite this in just a second here, but let's see what we've got there. Okay? And another reason we did this is now we see, going back to the total time with no wind, it was 2d over Vp. I sort of almost have that. I have a 2d on the top in the numerator, a Vp on the bottom, but I've got that extra term there. And so let's just rewrite it so we can look at it closely here. So after a few steps of algebra there, we find the total time for with wind is going to be 2d over Vp, and then this second part of the term here, which is the 1 over 1 minus Vw squared over Vp squared, like that. And all I did to go from here to here is just, write this part of the denominator as a separate factor there. And the reason I did that is to show very clearly, I have the 2d over Vp here, 2d over Vp, but it's not the same. I have an extra factor in here. So it turns out that when I've got the wind involved, going up and going back down, even though it's hurting going up, headwind, tailwind going back, it doesn't cancel out exactly. It actually is a difference with the wind involved such that you do not get your no wind time of travel for the round trip. You get a slightly different time. Note also that, and this is a good thing to check in these cases, you say, okay, this is the case with the wind involved. This equation should be true if there's no wind, right? Does it give us the right result? Well, if there's no wind, the velocity of the wind is 0. So this is 0, and I get 1 minus 0 here. Velocity of the plane is something. and then I get 1 divided by 1, so that's just 1, and I get 2d over Vp, the answer I get with no wind. So this is a more general equation I have derived. It works with wind, but it also works if I've got Vw equals 0 for the wind in there. So somewhat surprising result because, again, intuitively you think, shouldn't it cancel out? But let's think about this in terms of doing conceptual ideas like this or conceptual problems like this. Sometimes it helps to take an extreme case. So let's take an extreme case here. Let's say the plane velocity is 300 kilometers per hour, sort of a slow plane actually, I suppose, or 300 miles an hour if you want that, just or whatever you want to use for the velocity of the plane. And let's say the wind, okay, so this is going to be Vp. Let's say the wind is 299 kilometers per hour for the wind. Very strong wind, of course. Tornado wind, really. But again, it's just a thought experiment, like many thought experiments Einstein did. Maybe not quite sophisticated as some of his, but it's a thought experiment. Let's think about what happened here. Okay, just intuitively. So going up, the effective net velocity of the plane would be 300 minus 299. It'd be 1 kilometer per hour, okay, if it really could fly like that. So it'd be a very slow trip going up. And then on the way back down, the velocities would be 599 kilometers per hour, so about twice as fast. But by doing that, you can see, oh, it's going twice as fast going down, but it's not just going half as fast going up. It's going about 299 times slower than it did before. So it's not an equal situation in terms of going against the wind and coming back with the wind. You can double your speed in this case going with the wind, but you're slowed down many more times than just the doubling you get, much less than half the speed. And therefore you see that yes, there's a significant difference when the wind is involved. Okay? So the point being here, how does this apply back to the Michelson-Morley experiment? Well, in this case, essentially, this would work for light as well if there's a light medium, if the ether exists. Okay? So in other words, it'd be like sending a light beam against the ether wind and then sending a light beam with the ether wind. And if you could somehow see that difference in speed and detect it, then you could actually prove the ether exists or investigate the properties of the ether a little bit more. The problem is that the velocity of the Earth as it rotates around the sun, is about 30,000 meters per second, something like that. And that's still much, much less than the velocity of light. And so the effect, notice that when the velocity of the wind here is much less than the velocity of the plane, there's not much effect on the travel time. And that's the case with, even though the Earth moves around the sun at a relatively fast speed for most of what we're used to, certainly, that the velocity of light is so much greater than that this is a very small factor in here, and this is essentially 1, and therefore it's very difficult to see any effect. It does exist, it's very tiny, but with the experimental techniques they had, they weren't able to do it just from that alone. So they actually added on to this idea, and here's what they did, and that'll be the subject of our next part 3 for our video clips here. But essentially they said, okay, we'll do one up and back like this against the wind, but let's analyze the case where it's crosswind. So if the airplane or the light beam is going this way and the wind, whether the regular wind or the ether wind is going crossways against it, what happens in that situation? So we'll analyze that and then compare this situation with that situation and see what we can get out of it.